Okay, so by now you should know really what a fuel is, what a hydrocarbon is, and the fact that we can use those to obtain energy. And so in this video, I'm going to talk a bit about how we actually obtain the energy from those fuels. And the way we do that is via a reaction known as a combustion reaction. Combustion reaction. Okay, now we know that we burn fuels. So for example, in a car engine, the car will burn the fuels. However, that is not enough of a definition for us to say combustion. What combustion actually means is burning, so the burning of a fuel, burning a fuel in oxygen. So in oxygen. This part is very important. If we burn a fuel and we don't have any oxygen there, then we can't carry out a combustion reaction. Now there are different types of combustion. If we don't have enough oxygen, or there's an oxygen scarcity, then we can get incomplete combustion, and I'll come on to that a little bit later. But first of all, let's have a simple example of a combustion reaction with a fuel that you've probably seen before. And that fuel is methane. So methane is obviously the most simple alkane. You've only got one carbon there, so CH4. And we are burning an oxygen, so we are going to add oxygen. Okay, and from complete combustion, we are going to produce carbon dioxide and water. Okay, and because we're burning the fuels, we can write heat over the arrow like that. It's a condition, it's not a chemical, and so we write it over the arrow. Okay, now this is not balanced. So what we need to do here is we need to make the carbons, the oxygens, and the hydrogens have the same amount on each side of this equation. There is a trick for this, especially in combustion, and that is this. What we do is we look for the element in which it only appears in one compound on each side of the equation. So an example here would be carbon. Now carbon appears on the left hand side only in methane. It doesn't appear in oxygen. And on the right hand side it only appears in carbon dioxide. It doesn't appear in water. And therefore we know that the amount of carbon in carbon dioxide must balance the amount of carbon in the methane. And in both cases here, we only have one carbon in each, and so we can just leave that and say that those two are already balanced. So we're going to have one carbon from each. Now the next one, is it going to be oxygen or hydrogen? Hopefully you can see it's going to be hydrogen, because oxygen appears once on the left hand side, but it appears in carbon dioxide and in water, and therefore that makes balancing things fairly difficult. So I'm going to deal with the hydrogens. We have hydrogen here in water and also in methane. We have 4 hydrogens in methane and only 2 hydrogens in water. And therefore, in order to obtain 4, what we're going to have to do is multiply this water by 2. And now 2 lots of H2 is going to give us H4, as we have here on the left hand side. Okay, now lastly, we've done the carbons and the hydrogens. Now we can have a look at the oxygens. So on the right hand side we have 2 oxygens from carbon dioxide, and then 4 from water, because we have 2 waters. So we have 1 oxygen from each water, but we've got 2 of them. So 2 plus 2 is 4. On the left hand side we only have one oxygen molecule, that is, which contains 2 oxygens. Now how do we get from 2 to 4? We have to multiply the oxygen by 2 as well. Okay, so now this is perfectly balanced. We have the same amount of carbons, hydrogens and oxygens on the left hand side and the right hand side, and so we are happy in saying this is our equation. So let's use a different fuel, and you can pause the video after this and have a go yourself. So let's say we had C3H8, which is actually propane. So propane, burnt in oxygen. We can write heat over this arrow if we want. Heat will give us carbon dioxide and water. Now pause the video and have a go at balancing it yourself. Okay, so I hope you had a go. What I'm going to do is I'm going to write a list of carbon, hydrogen, oxygen for the left hand side, and carbon, hydrogen, oxygen for the right hand side. Once you get used to these, you don't have to do this, but some people do find it beneficial to have these written on paper. Right, so first we're going to start with carbons. On the left hand side, propane has 3 carbons, but on the right hand side, CO2 only has 1 carbon. And so how do we make 3 from 1? Well, we need to multiply that by 3. And that means that we are also going to multiply this whole molecule by 3. So 3 CO2s. And now the carbons balance. Okay, so we've got 3 and 3. Next, we're going to do the hydrogens. So there are 8 hydrogens in propane, but there are only 2 hydrogens in water, and obviously no hydrogens in CO2. So we have 8 hydrogens, 2 hydrogens. Now how do we get from 2 to 8? Well, we have to multiply it by 4. So 2 times 4 is equal to 8. And because we've multiplied this by 4, we need to multiply this molecule by 4. So 4 waters make 8 hydrogens. Okay, now how about the oxygens? Well, there are 2 oxygens here because of O2, but we now have multiplied these molecules, so we have 3 lots of CO2, which has 2 oxygens in it, so 3 times 2 is 6, plus 1 oxygen in each water. 1 lot of 4 is 4. So 6 oxygens from CO2, 4 oxygens from water gives us a grand total of 10 oxygens on the right hand side. Now obviously 10 is more than 2, and what do we have to multiply 2 by to get to 10? Well, 2 times 5 is going to give us 10, and now they are balanced. So now you can see 3, 8, 10, 3, 8, 10 on both sides. That means everything is going to be balanced, and so we've times this by 5, meaning we have 5 oxygens. And so that is the combustion of propane completely balanced, and we're happy. Now a quick note, one term you might come across is the term oxidation. Oxidation equals the addition of oxygen, or O2. So addition of oxygen in a chemical reaction. Drag this down, in a chemical reaction. And important to note, we can talk about carbon and hydrogen being oxidized in this case, because carbon and hydrogen here are not bound to any oxygens. We add oxygen, and now in the products, carbon is bound to an oxygen, and so is the hydrogen. So both the carbon and the hydrogen during this combustion have been oxidized. Now the opposite of oxidation is reduction, and that would be when oxygen is taken away in a chemical reaction. There are many different definitions of oxidation and reduction. This is one of them. You will see other ones with regards to hydrogen and with regards to electrons. So don't get those confused. Right, so what I'm going to move on to now is incomplete combustion. I mentioned this earlier, and we will get slightly different products. And that also means that our balancing of our equations is going to look slightly different. So, incomplete combustion. In a question, it will tell you what your product of incomplete combustion is going to be. Now, the theory behind this is that if we have a lack of oxygen, or there is not enough oxygen, okay, that means that we can't be generous and give each of our carbon 2 oxygens. So if you look up here, every carbon here has been given 2 oxygens to form carbon dioxide. But what if we didn't have enough oxygen to do that, but we were still burning it in some oxygen? I'm going to use the same compound just to show you. So C3H8 is propane plus oxygen. Now what can happen in this case is that we only have enough oxygen to afford 1 for every carbon. So we form CO rather than CO2. And you'll remember that CO is actually carbon monoxide. You will have heard of this gas before. It's not a very nice gas, and so obviously if we have incomplete combustion occurring in a car engine, we need to do something drastic to stop that, because carbon monoxide is toxic to us if we breathe it in. We actually do use catalytic converters to avoid this problem. But that is a topic for another video. What I'm going to do now is show you that we can balance it in exactly the same way. So again, I'm going to write CHO for the left, CHO for the right. Now we have 3 carbons on the left, 8 hydrogens and 2 oxygens. On the right hand side we have 1 carbon, we have 2 hydrogens, and we also have 2 oxygens. So we'll do the carbons first. Remember, there are 3 carbons here, and the only place on the right hand side is here, exactly the same as with complete combustion. So we need to make these equal. 1 times 3 will give us 3, and that means we need 3 molecules of carbon monoxide to balance. Next, hydrogen. We have 8 and we have 2, and so in exactly the same way, 2 times 4 will give us that 8. Therefore we have multiplied H by 4, so we need to multiply this entire molecule of water by 4. Now here is going to come the slight difference. 3 oxygens in the carbon monoxide, plus 4 oxygens coming from water gives us a grand total of 7 oxygens. Now we still have 2 oxygens on the left hand side, and so what can we times by 2 to get 7? Well, half of 7 is 3.5. So I'm going to say 3.5. I could have said 7 over 2. It's the same number. And so we need 3.5 oxygens. So let's just make room for that. 3.5 oxygens. And so that now looks different to the previous combustion because we had to balance the oxygens in a different way. However, the process is the same. The numbers are just going to be different. Now obviously if you are a person who doesn't like fractions or decimals, then please feel free to double everything in here, and we're going to get 2, 7, 6 and 8. I'm not going to write that out, but you feel free to do that if you like. Now one more type of incomplete combustion which I'm going to go over very briefly is one in which we have even less oxygen. For example, we'll use the same fuel again, why not? Propane plus oxygen. If there is barely any oxygen there, we may get no oxygens given to the carbon, but we still need the oxygen for the water. So we just have pure carbon being given off, and sometimes this is given off as soot. And so this is also a problem because it causes breathing problems. It can get clogged up in our lungs. But the balancing process is exactly the same as before. I'm going to do this one very quickly. So we need to balance the carbons, hydrogens, oxygens. 3 carbons here means we need 3 carbons on the right hand side. Hydrogens, we have 8 again, and so we need 4 waters because 2 times 4 equals 8, so we need 4 waters. And finally we need to balance the oxygens. Well, we have 4 oxygens because of the 4 waters, and we only have 2 oxygens on this side, so 2, we need to times that by 2 to get to 4. So in this case we only need 2 oxygens to balance there. Now I hope that's helped you with all the mathsy side of things with balancing equations, but lastly we're going to take a very quick look at the actual pollutants which are given off. So the first one was carbon monoxide. Carbon monoxide, and this is toxic. It's toxic because it actually gets into our blood. It gets into our blood, and of course we carry oxygen in our blood. And carbon monoxide stops us carrying much oxygen, which means that we're going to get out of breath very quickly, and it's going to cause major problems for the body. So in the blood, it reduces our oxygen, like that. Next we had just carbon, which we can call soot, or even just dust particles if you like. And this can cause breathing problems, and has even been linked to cancer. And so there are other particulates that can be given off, or compounds that can be given off, which we haven't spoke about because we don't actually write the equations for these. One of those is sulfur dioxide. Sulfur dioxide, or SO2. SO2. And sulfur dioxide is also toxic, but it is a very acidic substance when it is dissolved in water. And so it is acidic, And if this is given off as a gas, it can dissolve in the water in the air and come back down as rain. So it actually causes acid rain. And you should know that acid rain can cause damage to plants, it can cause damage to buildings, it will break down rocks, and that is known as corrosion. Something else it can do is, if this is in a car engine, it can actually cause corrosion within the engine, which can cause engine damage. That sulfur dioxide, it comes from impurities within the fuel. So fuels are never going to be 100% pure. They can be very close, but not 100%. And some of them will contain sulfur as an impurity, and others will contain nitrogen as an impurity, or both. So the next pollutant is nitrogen oxides. The reason it's oxides is because there's NO, we've got nitrogen dioxide, monoxide, nitrous oxide. There are a fair few, so we just group them as nitrogen oxides. Now these are not good for us either. These are acidic as well, so they can contribute to acid rain as well. They are also fairly toxic, and importantly, they trigger breathing problems that we've already got. And the main one is asthma. So if you're asthmatic and you breathe in nitrogen oxides, it will trigger a response which can result in an asthma attack. And so that is certainly not good. And so we'd rather not be releasing those sorts of things. So they are the pollutants that we can get from fuels. In another video, we will of course look at how we resolve those issues and how we stop those pollutants getting out. But I hope that's given you a good idea of what combustion is, how we actually write combustion in an equation and how we balance it, and of course what we can produce as a pollutant. So thanks for listening, and I'll see you in the next video.